Okay, now we're going to talk about quantitative data. So the first step in summarizing quantitative data is to determine whether the data are discrete or continuous. If the data are discrete and there's relatively few different values, right, then the categories of the data, which we'll call classes, the categories of data, will be the observations, just like it was in the qualitative data. If the data are discrete, but there's many different values, right? Lots of information, or if the data is continuous, then the classes are going to be created using intervals of numbers. Okay. All right. So here's an example. And we're still constructing frequency distributions and relative frequency distributions, right? It's just our data may look different. So the following sample represents the number of available cars in a household based on a random sample of 50 households. Construct a frequency and a relative frequency distribution. Okay, so here's our data. And when we look at it, we notice, oh, hey, really our values only go from 0 to 5. 1s, 2s, 3s, 4s. So this will not change from the frequency distribution table that we looked at in 2.1, right? So we put 0, 1, 2, 3, 4. That's our classes. Tally them up. Frequency, relative frequency. Okay, and here's a histogram, right? Constructed by drawing rectangles for each class of data. The height of each rectangle is the frequency, so the number of households with 2 cars was just over 20%, 21 or 22%. Now, here's the difference. Our frequency distribution tables are identical, okay? But this is a special kind of bar graph. If we had qualitative data, right, then we used a bar graph. If we have quantitative numerical data, we're going to use a histogram, which is a special bar graph where the bars have to touch. In a bar graph, the bars do not touch. And you have to have numerals in the horizontal axis, and they have to go in order, in numerical order, right? Okay, so the widths have to be the same size, just as in a regular bar graph, but the bars have to touch in a histogram. Okay, so there it is for the frequency, and here it is for the relative frequency. Look at the shape of the bars and the graph. It's identical, right? It better be identical. Okay, the only difference is we've got frequency here, relative frequency here. Okay, so classes are categories into which data are grouped. When a data set consists of a large number of different discrete data values, or when the data is continuous, we create classes by using intervals. So here's just an example. All right, so notice that the data are categorized or grouped by intervals or numbers. Each interval represents a class. Okay, there's 5 classes in this table, and this says it's the number in thousands. It's not really telling us what it is. Age of people, let's say in Texas, 25 to 34, right? 35 to 44, because you wouldn't want to put 25 and then have a rows if we just put 25, 26, 27, 28, all the way to 64. Look how unwieldy that chart would be, right? And you would lose your information in it. You might as well just have the raw data. Okay, the lower class limit, these are our classes. The lower class limit of a class is the smallest value, and the upper class limit is the largest value. So lower class limit of this is 25. Okay, lower class limit of this one is 35. Upper class limit is 34. Upper class limit of this one is 44. Okay, the class width is the difference between consecutive lower class limits. Now, don't subtract the 25 from 34. You've got to do it between two classes. 35 minus 25, 45 minus 35, any two classes. You could even do this, 54 minus 44. Ideally, do it somewhere in the middle also, and we'll see why in just a minute. Okay, this first class and second class may technically change because they can overlap. The classes can overlap. That's necessary to avoid confusion as to which class a data value belongs to. Excuse me. Sorry. And also the class widths have to be the same, with the occasional exception of the first or last one. Right? That's the only ones that might be different. Now, ideally, they wouldn't be either. But let's compare. Let's say we were doing a frequency distribution table for some qualitative grading data, A, B, C, D, F. Okay? Think about if we change that to numerical data, then a C would be 70 to 79, a B 80 to 89, but an A would be 90 to 100. Likewise, an F would be 0 to 59. So it is possible sometimes that we allow that first class and that bottom class to change width. So subtract any two from somewhere in the middle. Okay, so the following data represent the time between eruptions in seconds for a random sample of 45 eruptions at the Old Faithful Geyser in Wyoming. Construct a frequency and relative frequency distribution of the data. Okay, so to construct a frequency distribution, okay, first create classes of equal width, because I notice here that we've got a lot. Well, let's just see. Let's see what our smallest is. 698, 78, 95, 96, 672. Let me get a pen so we can keep up with this. Okay, we've got a 672. Here's a 726, 733, 735, 738. It looks like 672 to 738. If we did these individually, we'd have to have that many rows, from 672 to 738. So instead, I'm going to group them together in classes, right? So since we don't know now, let's just say, since I'm going from 672 to 738, let's just make our classes by tens, okay? And I don't really need to start at 672. I could. But just to make it easy, let's just say 670 to 79, 680 to 89, right? Okay. All right. So let's see. Okay. So here we are, right? It's just a regular frequency distribution table, except we've got classes. The class width is 690 minus 680 is 10, just like we said. Every one of them has to be the same, and none of them are overlapping. And then you just tally them up, anywhere between 670 and 679. Frequency, relative frequency. Don't forget, it's nice to have this bottom total. Okay? So formulas and procedures exist for creating frequency distributions from raw data, but they don't necessarily provide better summaries. There's no one correct frequency distribution for a particular set of data. However, some frequency distributions, can better illustrate patterns within the data than others. So use the distribution that seems to provide the best overall summary of the data. So the goal in constructing a frequency distribution data is to reveal interesting features of the data. But we also typically want the number of classes to be between 5 and 20. Once again, if our classes are too small, we lose the information, and if they're too large, we do also. Okay, so when the data set is small, we typically want fewer classes. When the data set is large, we typically want more classes. Okay, so for example, let's compare that. Let's see if that's where I'm at. Yeah, let's compare that to a display with a class width of 5. Here's what it looks like when our class width was 10. Okay, look at the tallies. Kind of tell the shape of the histogram if we laid it on its side. Okay, here it is with a class width of 5. Okay, so not that one's wrong. This does seem to be a little more convenient, right? Okay, so here's some guidelines for determining the lower class limit of the first class and the class width. All right, choose the smallest observation, which is what we did, or a number slightly lower than the smallest observation. Decide on the number of classes. Generally, there should be between 5 and 20 classes. And also, before we do this step, you might see, like we did first, well, how wide a span is there between the lowest and the highest value. Okay, the smaller the data set, the fewer classes you should have. Determine the class width by subtracting the largest and smallest data values and divide by the number of classes you want to have. Okay, round it up to a convenient number. Okay, so to draw the frequency histogram, use the frequency distribution. So I've copied it right here again, kind of squished together so it would fit on the page. And first label the lower class limits, right, of each class on the horizontal axis. Notice 670, 680, 690, 700. For each class, draw a rectangle whose width is the class width and whose height is the frequency. Okay, so it's exactly the same as our bar graph, except these values touch. Okay, if you're doing a relative frequency, same exact thing. The only difference is the scale on your vertical axis. Okay, now here is the frequency one with a class width of 5. Let's look at the difference in this shape and this shape. Once again, not necessarily that one of them is wrong. It's just, this one looks like maybe it gives us a better pattern. Okay. A stem and leaf plot is another way to represent quantitative data graphically. So a stem and leaf plot uses digits to the left of the rightmost digit to form the stem. Each rightmost digit forms a leaf. For example, if you had a data value of 147, 14 or 14 would be the stem and 7 would be the leaf. So let's do an example. Okay, we've got an individual is considered to be unemployed if they do not have a job but are actively seeking employment. The following data represent the unemployment rate in each of the 50 United States plus the District of Columbia in June 2008. Okay, that has just been repeated. Okay, right here. So all of that data wouldn't fit on the page with the instructions. So here's the data. Okay. Okay, and notice down here it says we let the stem represent the integer portion of the number and the leaf will be the decimal portion. Okay, for example, Alabama, the stem will be 4 and the leaf will be 7. Okay, and here is how they have it organized into a stem and leaf. So first thing, so let's go back and talk a little bit about the data first. So I would want to notice again my lowest and highest value. So I've got some 6s. I see, oh, there's a 6, 9. There's another 6, 9. Oh, there's an 8. Is there another 8? All right, so I'm going to go through 8. There's a 2. Okay. So my stems are going to be 2, 3, 4, 5, 6, 7, 8. Right? So here's what they've done. So I'm going to list those, put a vertical line, and then I just go through the data. And for every one, let me do this over here just so we can see. All right. So I'll just do it for a minute. So let's make it right here. 2, 3, 4, 5, 6, 7, 8. So here's a handy way to do it. Just go down the list. Okay, all right, now put your 7 here, 6.8, so an 8 goes here, 4.8, and 8 goes here, 5.0, I do put in the 0, 6.9, the 9 goes here, 5.1, so like that, right? So I don't have to scroll through here and find my lowest and on up. I can just go down the list as I get to it. 5.1, 5.4, okay, 4.2, etc., etc. Okay. And that'll give me this. Now, my final one, I'm going to put these values in order. Okay, and of course, it always has to have a title, and it has to have a legend or a key. And it'll always look like this. You just take the first value, okay, and say what it represents. Because for all I know, this could be 28, right, or 2.8, or various numbers of things. This book only allows you to have one value for a leaf, but technically, stem and leaves do exist where maybe this represents 3.22. 3.23, 3.88, right? So you have to have a legend. There's more than one option. All right. Notice that the stem and leaf plot looks much like a histogram turned on its side. So look, if I turn this on its side, I could see the shape of the histogram that's going to give me, right? Okay, the stem would serve as the classes, and the leaves would be the frequency. Okay, so therefore, it's important to space the leaves evenly. Okay, they've written them just boom, boom, boom right next to each other, but typically when you're writing them, you've got a little space between the numbers, so make your columns even. One advantage of the stem and leaf plot over frequency distributions and histograms is that the raw data can be retrieved from the stem and leaf plot. So in a stem and leaf, we could determine the actual maximum observation is 85 and the minimum is 28, okay? And we can see, oh, we've got 4 values that's exactly 4, okay? 2 values of 6.9. And we can't get that information from a histogram. We just know there's this many values between 5.0 and 5.9. but I don't know if they're all 5.5 or most of them are 5.0. I can't tell. But on the other hand, stem and leaf plots use their usefulness when data sets are large. Notice we had to record every single data item. Okay, and so a limitation of the stem and leaf plot is that we are effectively forced to use a class width of 1. Okay, 2, 3, 4, 5. Even though a larger width might be more desirable. Okay. Okay. So to construct a stem and leaf plot, the stem of the data value will consist of the digits to the left of the rightmost digit. So remember, this text is only allowing you to have one digit as your leaf. Everything to the left of that will be a stem. The leaf will be the value in the rightmost digit. Write the stems in a vertical column, excuse me, in increasing order. Draw a vertical line to the right of the stems. Write each leaf corresponding to the stems to the right of the vertical line. And within each stem, then rearrange the leaves in ascending order going up. Title the plot, include a legend. Okay, when data appear rather bunched, we can use split stems. Okay, the stem and leaf plot shown on the next slide reveals the distribution of the data better. As with the determination of class intervals and the creation of frequency histograms, judgment plays a major role. So no such thing as the correct stem and leaf. However, some plots are better than others. And here's what they meant. There it is, the same stem and leaf if we would have went from 3.0, well, we would have started, excuse me guys, I need a drink, with 2.5 to 2.9, 3.0 to 3.4, 3.5 to 3.9, right? So they split those stems in half. Okay? All right, one more graph. A dot plot. It's drawn by placing each observation horizontally in increasing order and placing a dot, or sometimes you'll see an X, above the observation each time it is observed. So for example, the following data represent the number of available cars. Hey, it's the same data. But now if they've displayed it in a dot plot, right, we already figured out that the values only go from 0 to 5. And then you just go along. Okay, so for 3, and you put a dot above it. 0, you put a dot above it. 1, you put a dot above it. 2, you put a dot above it. 1, you put a second dot. 1, another dot. 1, another dot. So as I said, a lot of times you'll see X's. X. I prefer that. It's still called a dot plot. Okay, just because it helps you, it helps me better in drawing it than having to put just dots above it. No, whatever, this book's using dots and dots only. Okay, so that's a pretty simple one, right? Once again, not really useful for very large displays of data. Okay, one way that a variable is described is through the shape of its distribution. So distribution shapes are typically classified as symmetric, skewed right, or skewed left. Okay, they're symmetric when you split the histogram down the middle and the right and left sides are basically mirror images, right? Like this one, both of these are symmetric actually. Okay, we call it a uniform distribution when the frequency of each value of the variable is evenly spread out across the values. So look, this is evenly spread out all the way across. bell-shaped, and they call it bell-shaped because if we drew a line connecting the middle of those, we get this bell, right? So both of these are considered symmetric, but one's uniform, one's bell-shaped. This one is skewed to the right because it's got a tail that goes off to the right farther than the left. This one is skewed to the left because its tail is pulled off to the left. Okay, so be careful. We do not describe qualitative, non-numerical data as skewed left, skewed right, or uniform. It's important to recognize that data will not always exhibit this behavior perfectly, okay? So we just try to identify the shape of the distribution with some flexibility. Okay? In addition, people may disagree on the shape since identifying it is subjective. So be careful about that. Makes it a little more tricky. Okay. For example, what do you think about this one? Identify the shape of the following histogram, which represents the time between eruptions at Old Faithful. Yeah, I'm just going to have to find what I feel like best fits that. And when you're thinking about drawing these curves, think about, I know I haven't here on each one, but kind of going through the middle of each one. Okay, so maybe skewed left, very subjective, right? Okay. Okay, last thing. If the value of a variable is measured at different points in the time, the data are referred to as a time series data. So a time series plot is obtained by plotting the time on the horizontal axis and the corresponding variable on the vertical axis. Then you just plot the points and connect them with line segments. Right? That's a time series plot. And as the name suggests, it's used for seeing patterns over time, right? Oh, between 91 and 98, the Dow was consistently rising. Oh, it dropped here between these years, etc. Okay, let me know if you have any questions.